Um, with that introduction, Professor Weitz, the floor is yours.
Okay, well, it's a pleasure and an honor to be here. A long way to come for us, but really a pleasure to do so. So, watch my time. Today I want to describe various types of, various applications of microfluidics. I'm going to talk about droplet microfluidics in particular. I'm going to talk about two generic applications, both materials and biotechnological applications. And let me say at the outset that all the work is done by many, many collaborators, students and postdocs who've been working with me in my lab over the years. So the last talk we heard about the applications of microfluidics for different organs on a chip, body on a chip, but mainly for diagnostics. And I would classify that as really all part of lab-on-a-chip applications. I always consider this, the lab-on-a-chip, the dean's best friend. Somebody comes and say they need more lab space. He says, well, just put it on a chip. And I'm going to talk about some lab-on-a-chip applications, but I want to actually begin with a completely different set of applications that we've also looked at, and that's material synthesis applications. By using the really exquisite control of the fluid flow possible with microfluidics, we can make new kinds of materials. And I want to spend most of my talk, in fact, emphasizing that. I'm going to tell you about making particles using droplets. So as I said, my focus is on droplet microfluidics. I'm going to use the droplets as templates to build new kinds of materials. The rationale is each droplet can be used as a template. Since it's a drop, I take advantage of the surface tension to maintain a spherical shape, and I build on that to make new structures, and I'm going to describe new functional materials. We can make them very, very monodisperse. We're doing things with really tremendous precision, tremendous exquisite control by using the control that we have with microfluidic structures. The question, of course, you should ask is, I'm making everything one drop at a time, and if I want to make bulk materials, can I possibly make enough materials to be useful? And I'd like to address that at the end of the talk and try and convince you that, in fact, or not in the middle of the talk, try and convince you that, in fact, we can. So we began this, this journey by not wanting to be limited by, in materials fabrication, not wanting to be limited by the traditional technology, particularly that's available to those of us at Harvard, by just going across the street from where my lab is to George Whiteside's lab. And he has invented this really wonderful technology of soft lithography that uses PDMS, that uses silicone, essentially, to make devices. It's a fantastic technology, and in my mind, it really democratized microfluidics by making it really accessible and easy to use, easy to make structures for everybody. But the problem is that it's not very friendly to a lot of different solvents if you want to make new kinds of materials. So we wanted to find something that would mimic the ease of fabrication of the soft lithography PDMS devices, but was more functional in terms of different types of chemicals. So we wanted to do something that was still made of, still easy to use, but was made of glass, just a very common material for making chemicals. And so we developed what we call capillary microfluidics. They have the advantage that they're three-dimensional, they're controllable, they're easily fabricated, and they have the same kind of simplicity that you do with soft lithography. So we start with just really the simplest thing. We go to our friends in the biology department. We take capillary tubes. They can be pulled, they're glass, so we can heat them up in the middle and extrude them to make very, very fine points. I'll show you examples of this, I hope, with higher resolution images. But to align the devices, we came up with a very simple strategy. The capillary tubes are well defined both on the inner diameter and the outer diameter. They're cylindrical in shape. So if we take a cylindrical shape and we thread it through a square capillary, that allows us to align them in a very, very simple fashion. Here's one geometry, the simplest geometry you can imagine. You have a cylindrical capillary tube inside a square capillary tube. The outer dimension of the cylinder is the same as the inner dimension of the square capillary, and you have 4 regions here where the cylindrical shape and the square shape are different. You can insert one fluid here, you can insert a second fluid here. The second fluid is tapered down to a very narrow orifice, and so you can very easily extrude one fluid into a second and make drops. This is what a device looks like. A device like this and much more complicated devices that I'll show you in a couple of minutes can be made in roughly half an hour by one of the skilled students in my group. It's all held together with our favorite material. I told you we like simplicity, so it's all held together just with 5-minute epoxy. And this is what it looks like. This is the creation of drops inside of a device like that. Here we're making drops of one fluid in a second. And if you look carefully, you won't be able to really distinguish the difference in shape. These are so uniform in shape. In fact, the first student who did this, I said, well, please, can you tell me what the polydispersity of the drops are? And he came back, he said it was about 3%. I said, well, how did you measure that? He said, well, I carefully took these images and I fit, using a image analysis program, I fit a circle to the shape and I measured how different the shapes were. I said, well, that's great, but what's the uncertainty of the image analysis program? He said, oh, it's about 3%. That was the uncertainty of the images. You just can't tell the difference in shape. They're so uniform. We can make them a little bit differently. We can flow the fluid. We call this dripping because it looks like a drip, drip, drip. We can flow the fluid a little faster. Then we make a jet. Now the drops are not quite as uniform in shape, but they always form drops. No matter how long the jet is, they always form drops. You can do different things. Just looking at the geometry, you can see that this is the geometry that I showed you. This is what we call the co-flow geometry, but we can turn it around. In fact, this was first done by one of my very excellent students. We told him, please do this, and he made a mistake. He did it the wrong way. And as always, when you make mistakes, you learn something new and interesting. So he made a mistake. He connected the inner fluid coming this way, but it still works. Now you get hydrodynamic flow focusing, and you get a fluid coming out of the other side. And this is what it looks like in actual practice. This is the forming drops. This is forming a jet. It works really well. But what's interesting about this geometry is now you have really a lot of space here. So because we can align the devices so easily, we add a second tube. Now we can align them very precisely, and we have a flow focusing geometry here, a co-flow geometry here, but now we have 3 fluids. And this is what it looks like in practice. Here you can see these 3 fluids. Maybe it's better to show it to you in this geometry where we're controlling the actual flow rates of the different fluids. And you can see that we can make drops inside of drops. We can make double emulsions with really exquisite precision. Just by changing the flow rates, you can change the relative size of the inner and the outer drops, and therefore control the size of the core and the shell. These already have interesting applications. Imagine I make a core shell geometry just like I showed you. Here's the outer fluid, this is the shell, this is the inner fluid, and let's just say that this fluid is water, and this fluid is also water, and this is some type of solvent in which we can put, for example, surfactants or diblock copolymers, some amphiphilic molecule. Those amphiphiles will go to the 2 interfaces. They'll coat this interface and this interface, and then if this solvent is slightly volatile, we can evaporate that, and we're left with a bilayer structure. So, for example, we can make a polymerisome made of diblock copolymers. We can make a liposome made of phospholipids. We can make a surfactant structure made with a bilayer surfactant structure. But what's really interesting is that this fluid and this fluid are completely different flow streams. So if we want to encapsulate something, which is what you often want to do with these structures if you're doing drug delivery, if you want to encapsulate something, you encapsulate absolutely perfectly because you're just using completely different flow streams. Here's an example where we made a polymerisome. These are made with biocompatible polymers. They're very difficult to make otherwise. This is PEG and PLA. You can see that you have a little excess. If you look carefully, you have a little excess of the polymer here. You always want to make enough that you ensure that you can get the droplets perfectly coated. Actually, watching this, the evaporation of the fluid is quite interesting. This is what you see. You see a de-wetting effect. But what you can see, if you look carefully, is that there's really a contact angle. So this implies that there must be some kind of interaction between the two surfactant layers. And if you vary the contents of the solvent, you can change the contact angle, you change the wetting angle, you can change the spreading. And if you look at the behavior, you find that the most stable structures always occur when the contact angle is the largest, which is 90 degrees. It can't be more than 90 degrees. And that just says that you get the largest interaction between the two shells, the two bilayers. In fact, if there's an adhesive interaction between them, they can't really be a fluid structure. And how can I tell that? Well, I can tell that by collapsing the structure. If they're a fluid, it should just collapse uniformly. If it's a solid, then as I collapse it, it will undergo a buckling. And you can see these things buckled. What I did was I just put a pressure on the outside so that I could draw water out, to put a large osmotic pressure on the outside to squeeze the structure down, and you get this buckling behavior. In fact, by measuring the degree of buckling, and when you see the buckling, here's the pressures that you're applying. You can see there are many atmospheres. By measuring this, you can actually calculate what the elastic properties of that shell are. Actually, looking at the way these things buckle, if I go and I replay this movie, you see what happens over time. It buckles, but if I wait long enough, you can see that it completely, the water is completely squeezed out. What that means is that any contents on the inside are also squeezed out. So not only have I showed a way of encapsulating something, I've also showed a way of releasing it. I just can use an osmotic pressure to squeeze everything out. But I can do something else. I could also take advantage of the fact that whatever the contents on the inside have its own osmotic pressure, and instead of squeezing it out, I can burst it by putting a very low osmotic pressure on the outside. So here I've used what we call osmotic shock. I've put low concentration of osmolytes on the outside. Basically, I just put pure water, and you can see that a small hole develops and everything escapes. This I've encapsulated a dye. If I allow it to open up and come back about half an hour later, all the dye is diffused away. I can't show you a fluorescence image. I have to show you this bright field image. It's actually interesting to watch this bursting, to watch this the explosion of the shells. Here's an example. Watch this particular structure as I expose it to very low osmotic pressure. You can see that it first grows, and then suddenly a little hole develops and it starts to shrink. If you watch this one over here, the same thing will happen. You see, the first thing is it grows, it's taking water in, and then it collapses as the hole develops. You can do other things. You don't have to evaporate the solvent. You can solidify the solvent. So here we used a low melting temperature wax. We use a triglyceride. We form this at high temperature, about 50 degrees C. It's fluid. Then we cool it down, and it solidifies. And now we can release it just by melting it. So here's an example where here we have some dye inside it, here we have some colloidal particles, and I'll just play this movie as we heat them up. You see the shell releases, the shell melts, and the contents are released. This actually has an immediate application. Very often, particularly with oncology, you want to deliver combinations of drugs. These drugs can be both hydrophilic and hydrophobic. You can incorporate a hydrophilic drug on the inside of the shell. You can incorporate a hydrophobic drug in the shell itself, and then you can release it just by melting. And if you do this, if you watch this, here we've just used a red and green dye, but you can see when they're released at exactly the same time at exactly the same point. So you can precisely control the relative concentration of the drugs in addition to delivering the drugs to the same location. Other things that we've done, Jörg Werner, who's now at BU, developed a swellable shell so you can change the pH using these types of materials. He developed shells that you can swell by increasing the pH and shrink by decreasing the pH. And you can see that you can then control the permeability of the shell. If you have a hydrogel, you can make it open and shut so you can release things in a controlled fashion over time. We had another visitor early on. One of the first visitors came to my lab from China, decided to make something slightly different, and he made a device that now he has two co-flow geometries, so he makes drops in one and produces them into the other. You see here's 3 drops going into this one. And now you can control the shape very nicely. And you control the number. Here you see the first one. I've watched this many times, so I know that very soon a second one will come, and quite quickly after this, a third drop will come. You can control precisely the number of drops. And so now you make what I call designer emulsions. So these are double emulsions, but now I can ask you, how many drops would you like? And you say 5. Well, I say, oh, good. Well, what size would you like? Big, small, large? We can control them really precisely. So Liang Yin showed me this, and I said, well, that's really nice, but we've already done this. What else can you do? Can you do something even more? So he looked at this. He said, well, look, I have 1 emulsion generator. I have 2 emulsion generators, 1, 2. What about this? So he added a 3rd emulsion generator. Now you make drops inside of drops inside of drops, again with the same really exquisite control. And so you can really make truly designer emulsions. Of course, you look at that and you'd say, well, only an academic would ever do something so stupid as that, as making toys like this. What could they possibly be useful for? So I challenged him, what could we use them for? And he made this structure. So look at this. This is a water and oil emulsion. These water drops have very, very delicate peptides inside it. They're all in oil continuous phase, but the oil has lots of surfactants, and the surfactants will denature the peptides. So to protect it, he built a hydrogel shell that in this case was thermosensitive. So if you heat it up, the shell starts to shrink. It tries to shrink. It tries to compress what's on the inside. It can't compress it, so instead it tears itself apart and it releases what's inside. So now you have a way of not only really precisely controlling the encapsulation, but you also can control the release. It's just now limited by your imagination of how you make these things. We did a lot of other things. Here's an example where we made bilayers of phospholipids. So we made, these are giant unilamellar vesicles. We can make them larger or smaller. These particular ones, I apologize for the contrast here. If you look carefully, you see just the remaining evaporation of the solvent here, and you can see the fluctuations. These are very, very delicate membranes. You can see the fluctuations, the thermal fluctuations of these membranes. Normally, these are structures, these are liposome structures. Small structures like this are widely used for drug delivery, have been used for 30 or so years. This is the normal structure that you make. where the inner and outer leaflets are exactly the same. But if you really want to become more sophisticated in making these structures, and this is becoming now increasingly utilized in drug delivery for many different applications. I won't describe all of them now. But what you often would like to do is make the different leaflets out of different materials. Well, this turns out to be very easy for us to do this. Now, instead of using just a single solvent, we use 2 layers of solvents. We use an inner solvent and an outer solvent. We put different phospholipids on the inside and on the outside. These on the inside will preferentially absorb on the inner interface. These on the outside will preferentially absorb on the outer leaflet, and you'll get an asymmetric structure. To test this, what we can do is just put something that will bind a dye. So we put some biotin, and we can put the biotin either on the inside or on the outside, expose it to a streptavidin conjugated dye, and just ask, do we get fluorescence? And so if we get if we have it on the inside, and we wash away the fluorophores, we won't get anything bound. If we have it on the outside, of course, it'll bind. And these are the results you can see here. There's very, very little when the biotin on the inside. There's very, very little dye that's bound, a little bit, but not very much. By contrast, when it's on the outside, you get a very large increase in the fluorescence. And if you do a calculation, you find it's about, the asymmetry is about 80%. It's consistent with just what diffusion would give you, because some of the inner molecules can diffuse to the outer layer. We can do other things. We don't have to use the same materials. We don't have to use phospholipids. So, for example, we've used diblock copolymers on the outside, phospholipids on the inside, or the reverse of this, and we get these asymmetric polymer phospholipid structures. I won't go into all the details of this. We did an exhaustive study, and we see that there's tremendous benefits in terms of improving both biocompatibility and integrity of the structure by having an asymmetric structure, with one side being soft with the phospholipids, the other side being much more rigid using the diblock copolymers. So I showed you now, I hope I showed you that you can make really interesting structures, but still you're making them one drop at a time, one particle at a time. They're very reproducible, but can you make them in large enough numbers? So can we scale it? Well, the obvious way is to parallelize it. I always make fun of my first student who did this. He's really a wonderful student. He did a lot of things. And he said, well, okay, can you make enough that we can make him experiments? Make me 2 devices out of these glass. So we came back an hour later, right, half an hour each, 2 devices. They work perfectly. I said, well, that's great. Make 10. Let's see if we can do 10. Came back a day later, right? Half an hour, 5 hours, had something to eat, got some sleep, came back, big smile on his face, and again, they just work perfectly. So now I said, well, that's really great, but let's make enough material to do something. Make me 1,000. And he looked at me, and he smiled, and he got up and walked out of my office. He's much too smart to do that. Instead, of course, what we have to do is use lithographic techniques. So we go across, we learn from George Weitz how to do this. And here's a device where we make these double emulsions, where we've just stacked 2 devices together. And we can stack 3 devices together, so we can make triple emulsions. In fact, the postdoc who was working on that did this. I said, well, what's the point? We've already made 3 triple emulsions. He said, so I'm going to show you. So he made a quintuple emulsion, a drop inside of a drop, inside of a drop, inside of a drop, inside of a drop. You just stack them along. Of course, that's not what we really want to do. We don't want to stack the emulsion generators in series. We want to stack them in parallel. And so here's a device where we made a multiple emulsion, and this has 25 emulsion generators. This is the size of an American dime. It's about a centimeter across for those who aren't familiar with it. And this starts making large amounts of material. But Esther Amstead came and she said, well, she really wanted to make a lot of material, so she made what she calls a millipede device. It's a device, each of these these tubes is an emulsion generator, and this has 1,000 tubes, 500 on each side. This is what it looks like. So now you can see it's starting to make really substantial amounts of material. So we wanted to prove that we could make enough material. We thought the ideal, it's still going to be fairly high value added material. The ideal thing would be to make materials for drug delivery. We're working on that now, but when we first started, we wanted to find something that had high value, but still was not as difficult to commercialize as drugs. And so the obvious thing is something that people pay a lot for is cosmetics. And so we started a company called Capsum to make cosmetics. This is the first material it made. It was sold by Amori Pacific in South Korea. Of course, the reason we did this is we had a postdoc who worked with Amori Pacific and asked us, could we make some material for him? This is what now a newer generation, this is actually a commercial system actually making large-scale droplets. And it made this material. It's called Skin Caviar Liquid Lift. It's sold by La Prairie. Those of you who know something about cosmetics will realize this is a very, very high-end Swiss cosmetics company. But I told you it's high value added. If you look at the web page and ask, what does it cost? This was, by the way, before the current inflation of post-pandemic. This was 50 mils, $500. So people pay a lot for these kinds of materials. Capsum actually developed another way of, this is another instrument that they developed another type of material that has a lot of its own interesting properties. With this they made this Hydro Beauty Micro Serum. It was sold by Chanel, and in the first 9 months, they made 1 million units in 9 months. Each unit sold for $100, so it's $100 million. It was the largest selling product introduced by Chanel, and Chanel liked it so much that they actually bought the company. They bought Capsum. Okay, so to me, that's proof positive that you can, by parallelizing, you can scale things up enough to make commercial types of materials. Let me now spend just a couple of minutes and tell you a little bit about our lab and chip applications. We heard a lot of really beautiful stuff for diagnostics in the last talk. We are interested in more biotech applications, taking advantage of the high throughput screening of applications that we have. The reason for this is very simple. If you do a very large number of experiments, you typically do that in a well plate. You put it, say this is a 384 well plate. You can do 384 experiments. Each experiment typically has between 10 and 100 microliters per experiment. We replace the wells by doing the experiments in drops. So each drop now becomes a reactor, and the size of these drops are about a picoliter. So the difference between a picoliter and a microliter is 8 orders of magnitude. That means that we can do 10 to the 8th more experiments than you can do with a well plate, given for the same amount of same volume of material. And if you're doing really high throughput experimentation, the most costly thing is the cost of the reagents. Now the reagents become much more affordable because we're using so much smaller reactions. So my rule of thumb is that we can work with drops that are between 1 and 100 microns, between a femtoliter, 10 microns is our sweet spot. It's about a picoliter per drop, or a nanoliter at 100 microns. And we do the experiments typically at 1,000 experiments per second. If my computer works, I'll show you some of the chips that we've made. We have to design chips to actually manipulate the drops. So here's a chip where we make the drops. We can split the drops. You can see we're splitting them into 2. We can split them into large and small, or we can split them many times. So now we're taking large drops. We're splitting them 1, 2, 3 times to make many small drops. We can extract small amounts of material. Here we're extracting a very small amount of material of this to do analysis further downstream. We tend to add the material back here. This was trying to make a large number of chemostats. We can mix drops. Turns out to be the most important thing. I don't know why the movies don't seem to play so well on my computer. But here we have an electric field that allows the drops to mix. There we go. We have another more recent invention we call a pico-injector. Here you can see that we're injecting a picoliter of fluid into each drop. Each drop is in itself a picoliter. We can do this not just once, but we can do this with many of them. Here we have 3 of them. We're injecting. We can control the injection by the electric field, so we can mix and match on a drop-by-drop basis what we're adding to the fluids. We can detect what's there, and if we really want to do something sophisticated, we have to select them. So this is one of the more sophisticated devices that we made, where you can see we have 2 different colors of drops. The dark ones are going here to the waste. We have a laser detector. Every time we see a drop we want, we put in a gradient of electric field, and we pull it down and separate the drops. Let me just give you very briefly one application. There are many kinds of applications. We probably spend most of our time using this kind of device. But one application is if you want to improve something, for example, a protein or an enzyme. This is a very commonly used enzyme. It's horseradish peroxidase. It's used in many biological experiments just as a marker because it takes a substrate. In this case, in the presence of peroxidase, it takes the substrate Amplex red and it turns it into resirufrin, which is a dye. So basically, it gives you an amplification with an optical signal. And the question is, can we somehow make this better? Well, it's very difficult to control the chemistry, but like all enzymes, it's coded by a gene. So it's made by using the information of its sequence with a gene. The problem is that the sequence space is enormous. So a typical enzyme, if it has 30 amino acids, it's got 300 amino acids. It's got 20 to 300. It's got astronomical number of possible things. So if you want to do something, if you want to improve it just by using the sequence space, it's actually, I can think of it as being more like an engineer or a physicist. I can think of it in terms of a fitness landscape. A fitness landscape is an energy landscape. If you're familiar with an energy landscape, it's an energy landscape turned upside down. You want to go from one point in space, say here where you are, you want to go up to here. And so the question is, can you take one leap? That means many different mutations, or do you do it in a step-by-step way by just going up the hills? If you do this, you'll never be able to find something really far away. The question is, in order to do this, you need many, many different variants. You need to make many different mutations to try and see it. So what you do is you do what's called directed evolution. Francis Arnold actually won the Nobel Prize a few years ago for inventing it. The concept is really very simple. You take the gene that codes for the enzyme. This is the parental gene, and you make a lot of errors. You reproduce it with a PCR, but you make many errors. So you do error-prone PCR, so you have many different mutants. Or you can take this and chop it up and recombine it. You can do a bunch of different ways, but essentially you make a library of mutated genes. And in this experiment, we did this by putting them into yeast. We took the mutated genes, we made it into a spherical plasmid. We put the plasmid into yeast, and we tricked the yeast, working with Dane Wittrup at MIT. We tricked the yeast to produce many copies of the enzyme on the surface. So the experiment then is, well, okay, this is just showing that we could do this. Any drop that has a yeast cell, we add the substrate, you see the fluorescence, and it's co-located, it's localized just in the drop. So the experiment is fairly simple. You take the library of mutations, you make it into plasmid. You will put one plasmid per yeast. You put one yeast cell per drop, and you just ask, do I get some signal? If I add the substrate, can I see something? In most cases, you can't see anything because you put a mutation and it doesn't work. And then if it works, you sort it out. And the nice thing is, because it's yeast, you can grow it up and you can do this sort many, many times. This is what the results look like. At first, when you do this, most of the mutations don't work. You're measuring the average level of fluorescence. It's very low compared to the wild type where everything works. But after you do a few rounds of sorting, you find something that works. And so we did this. We did one round. We just tried to ask, can we do reasonably well? But then we did something else. Once they're doing reasonably well, we added a second round of mutation, and we immediately found something that worked really well. So how can I describe what we did? What we're trying to do is we're going, as I showed you in my fitness landscape, we're trying to jump from one side to the next, from one mountain to the next. But what we did was we took a step along the way. We found something that worked reasonably well, and then we did it a second time to work even better. And you might say that you could do this. In fact, you can do this just in the more traditional ways. You can do it with a robot. Here it gives you the example of why you don't want to. If you do it with a robot, it would take about 5,000 liters of reagent. For the microfluidics, all the sorting took about 150 microliters. If you add up all the costs of what you were doing, or if you add up the time, it would take about 2 years to do the sorting. For us, just doing the sorting for the microfluidics was 7 hours, and the cost would have been about $16 million. This is, again, pre-inflation of the last couple of years, $16 million to do it. We tried to properly amortize the cost of what we were doing is about $2.50. Actually, you can do even better. I won't go through the details now, but rather than doing in yeast, you can do just an in vitro expression, and you can do a much larger selection. I won't show you the results of that, but clearly what you're trying to do is look at as many variants as possible. My estimate is when Frances Arnold did her Nobel Prize work, in one quantum of time for a graduate student, that's about 5 years, the graduate student could probably look at 1,000 different variants. When we did the yeast surface display a few years ago, we thought we could do about 10 to the 6 variants, and now with this in vitro technique, we can do 10 to the 12 variants. Really, the number of variants tell you how far in fitness space you can go. With this, by looking at 10 to the 12 variants, we can actually see 3 or 4 mutations away and still see something. So now we can find things that work completely different ways. We can really find new types of enzymes. Okay, with that, let me stop. I've tried to show you both the lab on a chip applications and the materials applications. And let me thank you for your attention and take some time for questions.
Thank you, Professor Weitz, for an enlightening talk. Now time for questions.
Hello, sir. My question is, how have you controlled the droplet volume in double emulsion system? Because the system, because you have taken a fixed needle size, where the droplet volume is varying. So how have you controlled the droplet volume?
You control the droplet volume by, it's made actually with a well-known hydrodynamic instability, the Rayleigh plateau instability. So it's a balance between viscous forces and surface tension forces. And that just sets itself as the droplet size. It's automatically controlled.
Hello, Professor. Thank you for a wonderful talk. So I have a question, like what is the typical material of the droplet emulsions that is being used? And the second question is, what is the typical life these droplets are being stable for without any variation in the size?
So, I mean, those are good questions. We use many different types of materials. One of our favorite for the biotech application, we use a fluorinated oil, but that's mainly because it's insoluble into the PDMS, so we can make the structures out of PDMS and make it with fluorinated oil. Also because DNA and nucleic acids don't dissolve in the fluorinated oil, so it's easier to keep things separate. But we've made it out of many different materials. And the stability of these are just emulsions, so the stability of an emulsion is always controlled by how good a surfactant you use. And so we spend a lot of time trying to design surfactants that keep things stable, but then are biocompatible or compatible with whatever we're trying to do.
Very powerful technology. And I'm wondering at the smaller end, so most droplets come in at 10 microns, 50 microns, but some applications that would be really nice to get into this 1 micron and below level. Do you have ways of achieving this? I mean, I know surface tension is against this whole endeavor, but are there capabilities in capillary microfluidics to break this sort of 1 micron barrier?
I mean, there's nothing that says you can't make microfluidic devices to make drops smaller than a micron, and people have done that. And it's the Navier-Stokes equations still work. There's no surface effects at a micron, even 100 nanometers. The real problem is clogging. And so the devices clog very easily. So you can try and avoid that. But we have a lot of other ways that we've learned over the years to make much smaller structures. Right now, like many people, we've become very interested in trying to look for the next level of these lipid nanoparticles that sort of saved the world with the mRNA vaccines. And for that, we have different ways of making them.
Yes, sir. One simple question. So, with what device you maintain the flow? So there will be a lot of fluctuations now while you create these droplets.
I'm sorry, you say there are fluctuations?
Yeah, with what device you maintain the flow?
I mean, the fluctuations are not so bad because everything is really so precisely controlled by the microfluidics. Everything is perfectly laminar. It's actually, if we want to go to mix things by increasing the Reynolds number, it's difficult. There are ways of doing it, but it's more difficult. But we don't seem to have the problems with fluctuations or variations. I think that's what you're asking.
Yeah. I mean the flow maintaining device which you used.
The flow needs to be very steady, yes. But that's fairly easily achieved using syringe pumps.
Just the usual syringe pump.
Yeah, or a controlled pressure.
Thanks for the talk. Great fan, big fan. So I had a question since you showed such precise control over making bilayers and even inserting them into other things. Have you considered making proto-cells and just studying how life would have emerged?
The answer is yes. We did that, actually, I had a student who did that even before we had figured out all this microfluidic stuff. The problem with that is, 2 or 3 fluids is not going to come near to what you need if you want to make something that mimics a cell. So the challenge there is not so much to have absolutely precise control and be able to make everything exactly the same, but rather to know exactly what kind of materials you want to do. And so we do that on a different side of what my group studies. And we were very interested in looking at different proteins in cells and trying to reconstitute things.
On another, as an extension, have you also tried, since you spoke about in vitro transcription or translation, encapsulating these machinery within the droplets and then trying to make something dynamic, which could respond to some environmental stimulus or something?
Again, we've done that more for the having a responsive material for the controlled release for the materials property to make things like that, to put transfection and things like that. That we're interested in, but that's much more along the lines of what we're working on for drug delivery. So we'll make the materials from the with the microfluidics and use that to transfect cells, for example. We do a lot of work on that.
Thank you.
All right, so more questions probably can go to coffee break. Thank you, Professor Weitz, for a nice talk. And we have a small token for you. And thank you.
Thank you so much.
You can look at the camera.